Alright, silly people, here's the situation. We got this silly little matrix that we're going to be doing some stuff to. The first thing that we're going to do to it is actually just get the determinant of it and the trace of it. So the determinant is going to be just setting up the absolute value of that guy. So it's 2 times 2 times 2 makes 8, and then minus 1, and then also minus 1, and then minus 2, and then also minus 2, and also minus 2. So that is going to be 8 minus 1 makes minus 2, minus 2 minus 2 makes minus 4, and then minus 2. So it looks like 0. So that's fun. Also see the trace of the matrix is just adding up all of the diagonal elements. So it's 2 plus 2 plus 2, so 6. Right? The diagonalized form of that matrix should give the same determinant and the same trace. So we better find what the eigenvalues are and check it against that. So setting up the eigenvalue equation, we're going to find the determinant of 2 minus lambda minus I1, I2 minus lambda minus I1, I2 minus lambda, and set that determinant equal to 0. And that determinant is looking like 2 minus lambda to the third, minus 1, minus 1, and then minus 2 minus lambda, also minus 2 minus lambda, also minus 2 minus lambda. So it looks like the equation is 2 minus lambda to the cubed minus 2 minus 3 times 2 minus lambda. That is a pretty gross little like equation that you have to solve there. But if we fully expand it, you'll see that it's not nearly as gross as you think it is. So just expanding the 2 minus lambda squared term, we've got 4 minus 4 lambda plus lambda squared. And then this is minus 2 minus 6 plus 3 lambda equals 0. And then expanding the 2 minus lambda into the squared term, we got 8 minus 8 lambda minus lambda cubed, or actually plus 2 lambda squared, the way that I'm doing it. And then minus 4 lambda plus 4 lambda squared minus lambda cubed. And then on the outside, it's minus 8 plus 3 lambda. So we've got 8 minus 8 makes 0, minus 8 minus 4 plus 3 makes minus 9, right? Yeah, minus 9 lambda. And then 2 and 4 makes 6 lambda squared, and it's a minus lambda cubed equals 0. So see how one of the solutions to that is just plugging in 0, since you don't have a constant here. So we're going to say that that's lambda 1. Lambda 1 equals 0. And then we can factor that out of this equation to get minus 9 plus 6 lambda minus lambda squared equals 0. That can be factored, especially if we switch the signs around. So if we instead, or actually let's just factor it like this. Why not? I think you'll find that lambda minus 3 times 3 minus lambda will work. So it's lambda times 3 minus lambda times minus 3. That gives you 6 lambda. And then the minus 3 times 3 term gives you the minus 9. And then the lambda times the minus lambda term gives you minus lambda squared. So that is a good factorization, which is telling us that there is another solution at lambda equals 3, and also another solution at lambda equals 3. So this is actually a degenerate Hermitian matrix here, the diagonal form of which, or the diagonalized form of it, will look like 0, 0, 0, 0, 3, 0, 0, 0, 3. which if we take the determinant of this guy, it should match up with the determinant of the old original matrix that we got. The determinant of that is 0 times 3 times 3, so 0. The determinant was 0, right? Yes. And then the trace was 6 for the matrix we were given. 3 plus 3 is 6, so the trace of this guy is also 6. So these are both fine. Now we actually have to find the eigenvectors of it, given the eigenvalues that we found, and find the matrix which diagonalizes the original matrix T from those, which is an issue because we have two eigenvalues that are equal to each other, so finding the eigenvectors is going to be weird. But just setting up the eigenvector equation, we've got 2 minus I1, I2 minus I1, I2, that is just the original matrix, times arbitrary eigenvector with elements alpha, beta, gamma, is equal to 0 times alpha, beta, gamma for lambda 1, so just 0 on the right hand side. That's telling us that 2 alpha plus I beta plus gamma equals 0. And also minus I alpha plus 2 beta plus I gamma equals 0. If you multiply the second equation by I, you actually get alpha plus 2I beta minus gamma equals 0. And you can add these equations together to get 3 alpha plus 3I beta equals 0, which is going to tell you that alpha equals minus I beta, or equivalently, you get I alpha equals beta. And yeah, that's fine. So that is going to tell you that gamma is free, but beta is equal to I alpha. I don't even know if gamma is free. Alpha should be free. If you plug this guy back into this equation over here, then you have 2 alpha plus I squared alpha plus gamma equals 0. Then you have 2 alpha minus alpha plus gamma equals 0. So you have alpha equals minus gamma. Okay, so whatever. That should tell you, if you set alpha to 1 for V1 with normalization N1, you get a 1 and a minus 1 and an I for the first eigenvector, which we should normalize this, right? So it's going to be setting the inner product of V1 with itself to 1. You'll find that N1 squared 1 minus I minus 1 times the column vector 1 I minus 1 gives you N1 squared times 1 plus 1 plus 1. And you set that equal to 1, and you find that N1 is equal to 1 over root 3. So that gives you the form for V1, right? That's telling you that V1 is 1 over root 3 times that thing. Okay, now you can go about finding V2 and also V3 through a weird little method. So setting up the eigenvector equation again, like this. This is just the original matrix again, times eigenvector V2, which I'm going to have the elements called A, B, and C. That has to be equal to the second eigenvalue, which was 3 times the same vector. So it looks like we're going to be solving the equations. 2a plus ib plus c equals 3a, and also minus ia plus 2b plus ic equals 3b, and a minus ib plus 2c equals 3c. Now I'm going to tell you that all of these equations are the same equation. If you solve this guy for a, it looks like ib plus c equals a. Did the same thing here just by multiplying by overall I, and then canceling out b's on either side. You get I plus, or it's actually a minus c equals ib, which is the same as this equation. And then on the third one, if you just cancel out c's on both sides, it's literally already the same equation, a minus ib equals c. These are all the same. So that's kind of strange. So you have choices when it comes to this. A first really good choice is to set c equal to 0. That's a cool choice. That's going to make it so that a is equal to ib, or rather minus ia equals b, right? That's equivalent. And so you can write v2 equal, what's that, n2 times 0 down here, and then 1 we're going to choose for a, and then it'll follow that b is minus I. And then we can normalize that, but it should be fairly obvious that the normalization factor to go on that is just 1 over root 2, right? Cool. What is V3? Well, my methodology for finding this was that saying that V2 has to be orthogonal to V3, right? And also same thing with V1 has to be orthogonal to V3. And V1 and V2 thus far have both had an imaginary component in the second element. So V1 had I in the second element, V2 had minus I in the second element. So I'm going to say just set up V3 like this, N3 A, and then fix the second element to I, and then the third element will follow from these same equations that we've set up, right? So with that in mind, A is equal to minus I squared equals C, and so A plus 1 equals C, so yeah, C equals A plus 1. So if we set A to 1, you'll find that this is N3, 1, I, 2. And then the normalization for that, we'll just go ahead and do it by taking the inner product of it with itself and set it equal to 1. So you get the normalization constant squared, so N3 squared, times the row vector A minus I, or not A minus I, 1 minus I, 2, times the column vector 1, I, 2. That's going to give you N3 squared, 1 plus 1 plus 4. Set that equal to 1. So clearly N3 is just 1 over root 6. And so V3, you can write it like 1 over root 6 times 1i2. Okay, that's pretty cool. Let's check explicitly that this is actually orthogonal to both V1 and V2. So V2 inner product with V3 will be 1 over root 6 times the row vector 1i0 times the row vector or column vector 1i2. That's going to give you 1 over root 6, 1 minus 1, so 0. That's good. Also check V1 inner product with V3. That is going to give you, let's see, the normalization on V1 was 1 over root 3, right? Yeah. So it's 1 over root 3 times 1 over root 6 gives you 1 over root 18, and it was, what was V1? It was 1 I minus 1. So then the row vector will be 1 minus I minus 1. Right. Yes, okay, cool. Then the column vector, row 3 is again 1i2. That's going to give you 1 over root 18. 1 plus 1 minus 2. That is 0 as well. So both of these are orthogonal, and V3 looks correct, so we can keep going and writing the inverse of the matrix, which will diagonalize T. It will be formed by the columns of it will be formed by the eigenvectors, right? So let me write a big matrix here. 6 lines, roughly. And so V1 we already said was 1 over root 3. I over root 3 minus 1 over root 3. And then V2 ended up being 1 over root 2 minus I over root 2, right? Just making sure. Yep. And then 0 down here. And then V3 was 1 over root 6. I over root 6, 2 over root 6. Okay. We can simplify that by factoring out a 1 over root 6, looks like. So root 6 over root 3 is root 2, so that should be root 2, I root 2, minus 1 root 2, so just minus root 2. And then root 6 over root 2 makes root 3, so this is going to be root 3 minus I root 3, 0, and then 1 I 2. Cool. The inverse of that is going to be the Hermitian adjoint of that, so it's going to be just root 2 root 3 1 minus I root 2 I root 3 0. That's not right. It's going to be minus I here. The 0 is going to be here because it's minus root 2 and then 2 down here. Right. Then we will check explicitly that S, T, S inverse does actually give us the diagonalized form of T. So just setting it all up and also making sure to write the normalization factor on that, it's 1 over root 6. Setting that up, we got 1 over root 6 times root 6 makes 1 over 6. And then S is root 2 root 3 1 minus I root 2 I root 3 minus I minus root 2 0 2. T was is 2 minus I 1 I 2 minus I 1 I 2. And then S inverse was root 2 I root 2 minus root 2 root 3 minus I root 3 0 1 I. That was a gross little I. And then 2. Okay. Now we will multiply these together. I'm just going to multiply the latter 2 and hold on to the first for now, like that. So the two matrices multiplied together. Looks like it's 2 root 2 minus root 2 minus root 2, and then 2 root 3 plus root 3, and then 0, and then 2 minus 1 plus 2, This is minus I root 2. This is plus 2I root 2. This is minus I root 2. And then here, minus I root 3, minus 2I root 3, and then 0. Or actually, not I there. It's minus I plus 2I plus 2I. And then we have root 2 plus root 2 minus 2 root 2 I root 3 plus root 3. No, that's not right. It's 1 times root 3, so root 3, plus root 3. No, it's minus root 3. That's what it is. And then, yeah, the last element of that is 0, and then it's 1 times, or 1 plus 4. Okay. Arithmetic, everybody. Or I guess it is matrix arithmetic, so I can't be too upset that it ended up being complicated. Stop. Okay. Simplifying. 2 minus root 2 is 0. Minus I root 2 plus 2I root 2 is 0. Root 2 plus root 2 minus 2 root 2 is 0. 2 root 3 plus root 3 is 3 root 3. Minus I root 3 minus 2I root 3 is minus 3I root 3. Root 3 minus root 3 is 0. 2 minus 1 plus 2 is 3. Minus I plus 2I is 3I. And then 6. And then we can multiply these guys together. So this is, I can tell you the first column is 0 for free. And then it's 2 times 3 root 3, or root 2 times 3 root 3. So 3 root 6. And then it's minus, or positive I squared 3 root 3. So minus 3 root 6. And then 0. And then this is 3 root 2 plus 3 root 2 minus 6 root 2. Then we've got 3 times 3, so 9 plus 9, and then 0. And then this guy is 3 root 3, and then minus 3 root 3. Yeah, minus 3 root 3 here, and then 0. And then this is 3 root 3 minus 3 root 3, 0. And then finally 3 minus, or plus 3 plus 12. Okay. Funny little stuff there. A lot of that is 0. The first row, or the first column was 0, because it was all being multiplied by 0. 3 root 6 minus 3 root 6 is 0. 9 plus 9 is 18. These terms cancel at 0. Why do I have a 3 root 2 and then a 3i root 2? I don't think I did that term right. I'm pretty sure this should be also a root 2. Let me just make sure. Yes, that should be a root 2. So these terms added together cancel out this one, so this one's 0. These terms are canceling it out, so it's 0. So 3 plus 12 also makes 18. 18 over 6 is 3. Yo. That's exactly what it should be. Okay. Good stuff.